Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Properties of magnets. Magnets have two poles as a north and a south at the end of the magnets. Magnetic forces are the strongest at north and south poles. When two magnets are held close together, there will be a force between the magnets. Unlike poles attract, like poles repel. Magnetic materials. They will always be attracted to a magnet, and can be magnetized. Magnetic materials contain iron, nickel or cobalt. For example, steel is mainly iron. There are two types of the magnetic materials as hard magnetic materials such as steel are difficult to magnetize, but do not readily lose their magnetism. They are used for permanent magnets. Soft magnetic materials such as iron are relatively easy to magnetize and easy to lose magnetism, so their magnetism is only temporary. They are used in the cores of electromagnet and transformers, because their magnetic effect can be switched on and off, or reversed easily. Non-magnetic materials are not attracted or repelled by magnets, and cannot be magnetized. They include all metals that do not contain iron, nickel or cobalt, and all nonmetals. To determine whether a material is a magnet, a magnetic material, or a non-magnetic material, bring it close to a known magnet. If it can be repelled by the known magnet, then it is a magnet. If it can only be attracted, and not repelled, then it is a magnetic material. If it is not affected, then it is a non-magnetic material. For example, there are three unknown metal bars and a known magnet. When a north pole is brought near the end A, they attract each other. Then the north pole of a known magnet is brought near the end B, they attract each other again. This shows that bar AB is a magnetic material. When a north pole is brought near the end C, they repel each other. This shows that bar CD is a magnet, and the end C is north pole, then the end D is south pole. When a north pole is brought near the end E, so nothing is happening. This shows that bar EF is non-magnetic material. Magnetizing the magnetic materials. Magnetization is the process of inducing magnetism in magnetic materials. There are three ways to magnetize the magnetism of a magnet. Induced magnetism of magnetic materials by a strongly magnet. The iron and steel can magnetized when placed near a magnet, but its magnetism is usually weak. When an iron bar and a steel bar are brought to attract with a north pole of a strong magnet, the iron and steel are magnetized. These ends of iron and steel are south poles and another end of both are north poles. When the iron and steel are brought away from the north pole of the strong magnet, the iron loses its magnetism. The steel is still permanently magnetized. Magnetizing a magnetic material by stroking it with a magnet. This method can be magnetized more strongly. A steel bar is stroked with the north pole of a magnet in one direction. This end of the steel bar is magnetized to be a south pole. This end is magnetized to be a north pole. When a south pole is stroked along the steel bar in same direction, this end of steel is magnetized to be a north pole. And this end is magnetized to be a south pole. When a north pole is stroked along the steel bar in the opposite direction, this end of steel is magnetized to be a north pole. And this end is a south pole. Magnetizing a magnetic material using direct current. This method is one of the most effective ways to magnetize a material. A steel nail is inserted into a long coil of wire. The DC power supply is turned on to pass a large direct current through the coil. To keep a steel nail inside a coil, the current generates a magnetic field that magnetizes the steel. This end is magnetized to be north pole. And this end is magnetized to be south pole. We will explain this process in more detail in the section of 4.5.3 Magnetic effect of a current. Demagnetizing the magnets. Demagnetization is the process that destroys the magnetism of a magnet. There are three ways to demagnetize the magnetism of a magnet. Demagnetization by heating. To heat a magnet with a fire until it demagnetizes. Demagnetization by hitting. To hit a magnet by a hammer with a moderate amount of force until it demagnetizes. Demagnetization by alternating current. To insert a magnet into a long coil. Turn on the AC power supply. Slowly pull the magnet away from the coil until it is completely outside of the coil. The large alternating current generates the changing magnetic field to demagnetize the magnet. Don't keep a magnet in the coil, because this cannot be demagnetized to complete. Magnetic field. All magnets are surrounded by a magnetic field. The magnetic field is defined as the region in space where magnetic material experience a force. Magnetic field lines are imaginary lines that represent the direction and strength of a magnetic field. Magnetic field lines run from the North Pole to South Pole. Magnetic field lines cannot cross each other. Strong magnetic field strength where lines are close each other. And weak magnetic field strength where lines are far apart each other. The arrow is indicated the direction of force acting on the north pole of a magnet at that point. The magnetic field lines around a bar magnet. Magnetic field lines run from north to south. Magnetic field lines are very close each other at the north and south. This shows that the magnetic field strength is strong. Magnetic field lines are far apart where further from the magnet. This shows that the magnetic field strength is weak. The magnetic field lines pattern around two magnets with opposite poles. The magnetic field lines pattern around two magnets with same poles. This is neutral point, which has no magnetic field strength and no magnetic force to act on the magnetic material. A uniform magnetic field between two opposite poles. Magnetic field lines run from north to south poles. Magnetic field lines are parallel and same space each other. This shows that the magnetic field strength remains constant. The magnetic field lines around the Earth. Inside the inner core contain the iron and nickel, which are the magnetic material. This causes the core of the Earth is a magnet. The north pole of Earth is south pole of the magnet, and south pole of Earth is north pole of the magnet. The magnetic field lines of the Earth run from the south to north of the Earth. A needle of the compass is always pointed to the north pole of the Earth. So, the needle is a magnet. And the arrow of the needle is north pole magnet, which attracts to the south pole of Earth's magnet. This shows that the needle of a compass will always point in the same direction of the magnetic field line. Plotting the magnetic field lines around a bar magnet. Using iron fillings. Place a piece of paper, or glass, on top of the magnet. Gently sprinkle iron fillings on top of the paper or glass. Now carefully tap the paper or glass to allow the iron fillings to settle on the field lines. Using a compass. Place a magnet on top of a piece of paper. Place a compass at the one end of the magnet. Draw a dot at the tip of the needle. Then the compass is moved so that the needle lines up with the previous dot, and so on. When the dots are joined up, the result is a magnetic field line. More lines can be drawn by starting with the compass in different positions. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Magnetic field around a conducting wire. When a current flows through a conducting wire, a magnetic field is produced around the wire. The shape and direction of the magnetic field can be investigated using plotting compasses. The compasses would produce a magnetic field lines pattern that would look the following. The magnetic field is made up of circles. As the distance from the wire increases, the circles get further apart. This shows that the magnetic field is strongest closest to the wire and gets weaker as the distance from the wire increases. The right-hand grip rule can be used to work out the direction of the magnetic field. Thumb point along the direction of the current. The curled forefingers give the direction of the field. Reversing the direction in which the current flows through the wire will reverse the direction of the magnetic field. Increasing the amount of current flowing through the wire will increase the strength of the magnetic field. This means the field lines will become closer together. Magnetic field around a solenoid. When a current flows through a wire that is looped into a coil, the magnetic field lines circle around each part of the coil, passing through the center of it. When a current flows through the wire that is coiled to form a solenoid, this causes the magnetic field strength to increase. Stronger the magnetic field strength, greater the number of field lines. The right-hand grip rule can be used to work out the direction of the magnetic field. The curled forefingers give the direction of the current in the solenoid. Thumb point along the direction of the field. This end of the solenoid is North Pole. This end is South Pole. The magnetic field pattern will look the following. The magnetic field around the solenoid is similar to that of a bar magnet. The magnetic field inside the solenoid is strong and uniform. Reversing the current direction reverses the direction of magnetic field. Adding more turns increases the solenoid's magnetic field strength. The electromagnet. A solenoid can be used as an electromagnet by adding a soft iron core. The iron core will become an induced magnet when current is flowing through the solenoid. The magnetic field produced from the solenoid and the iron core will create a much stronger magnet overall. Iron core is the soft magnetic material. It is easily magnetized and demagnetized, allowing the electromagnet to be switched on and off by turning the current on and off. When current flows, a magnetic field forms around the electromagnet. When it is switched off, the field disappears. Changing the direction of the current also changes the direction of the magnetic field produced by the iron core. The strength of an electromagnet can be increased by increasing the size of the current, which is flowing through the wire, increasing the number of coils, adding an iron core through the center of the coils. Electromagnets are used in a wide variety of applications, including electric relays, used in electric bells, electronic locks and others. Loudspeakers and headphones will be explained in the next section. Electric bell. An electric bell relies on an electromagnet to function. When the button switch is pressed, a current passes through the electromagnet, creating a magnetic field. This attracted the springy metal, causing the hammer to strike the bell. The movement of the springy metal breaks the circuit by separating the contacts. This stops the current, destroying the magnetic field, and so the springy metal returns to its previous position. This re-establishes the circuit, and the whole process starts again. Force on a current-carrying conductor wire. When a current flows through a wire, it creates a magnetic field around the wire. This magnetic field interacts with the magnetic field of a magnet, producing a force to act on a wire upward. This causes the wire to move upward. The Fleming left-hand rule helps determine the direction of magnetic force on the wire. The index finger points in the direction of the magnetic field. The middle finger points in the direction of the current. Thumb points in the direction of the force, or motion. All three fingers are perpendicular to each other. The force is maximum when the current flows perpendicular to the magnetic field. The force on a wire decreases when the current flows at the angle to the magnetic field. And there is no force on a wire when the current flows parallel to the magnetic field. The magnetic force is always perpendicular to both the current and the magnetic field. The direction of force on the wire can be reversed by reversing the current, reversing the magnetic field. If both the current and magnetic field are reversed at the same time, the direction of the force remains the same. The magnitude of magnetic force can be increased by increasing the current, increasing the magnetic field strength by using the stronger magnet, increasing the length of the wire that interacts with the magnetic field by adding more loops. Loudspeakers and headphones. Loudspeakers and headphones convert electrical signals into sound. A loudspeaker consists of a coil of wire, which is wrapped around one pole of a permanent magnet. The loudspeaker is connected to an amplifier that provides an alternating current. This alternating current flows through the coil, creating alternating magnetic field around it. The alternating magnetic fields interact with the field of permanent magnet, causing a force to be exerted on the coil. As the constant change in the magnetic field direction, the exerted force on the coil will constantly change direction, causing the coil to oscillate. The oscillating coil then causes the paper cone to oscillate. This makes the surrounding air to oscillate, creating compressions and rarefactions, forming sound waves. Force on the moving charged particles in the magnetic field. When a negatively charged particle travels opposite to the current flow, a negatively charged particle travels to interact perpendicular to a uniform magnetic field directed into the page. This interaction creates a magnetic force being exerted on the particle, directed downward and perpendicular to its motion. Applying the Fleming left-hand rule, with your index finger pointing into the page along the magnetic field direction, and your middle pointing to the left along the current direction, you see that your thumb points downward, indicating the direction of force acting on the negatively charged particle. This force always acts on the particle at a right angle, causing it to move in a circular path. When the negatively charged particle leaves from the magnetic field, it moves in a straight line, because of the absence of the magnetic force. When a positively charged particle travels in the same direction as the current flow, a positively charged particle also interacts perpendicularly with a uniform magnetic field directed into the page. This interaction creates a magnetic force acting on the particle, directed upwards and perpendicular to its motion. Applying the Fleming left-hand rule, with your index finger pointing into the page along the magnetic field direction, and your middle pointing to the right along the current direction, you see that your thumb points upwards, indicating the direction of force acting on the positively charged particle. This force always acts on the particle at a right angle, causing it to move in a circular path. When the positively charged particle leaves the magnetic field, it moves in a straight line, because of the absence of the magnetic force. The DC motor without the split ring commutator. It is the device which changes electrical energy to kinetic energy. The simple DC motor consists of a coil of wire, which is free to rotate, positioned in a uniform magnetic field. When the current is flowing in the coil at right angle to the permanent magnetic field, the current creates a magnetic field around the coil that interacts with the field from the permanent magnets. This produces the forces being exerted on the coil, causing it to turn. The direction of the force can be determined using Fleming's left-hand rule. As current will flow in opposite directions on each side of the coil, the force produced from the magnetic field will push one side of the coil up and the other side of the coil down. This will cause the coil to rotate, and it will continue to rotate until it is in the vertical position. In the vertical position, the magnetic forces on each side of the coil act upward and downward, cancelling each other out, resulting in no net turning effect. However, the momentum, or inertia, of the coil keeps it turning until the magnetic force takes the moment of force in the opposite direction again. This causes the coil to oscillate with a small angle. To prevent this and ensure continuous rotation in one direction, a split ring commutator is used. This device reverses the current flow in the coil as it reaches the vertical position, effectively changing the direction of the magnetic forces and pushing the coil to continue rotating. The DC motor with the split rings commutator. This is the split ring commutator. It swaps the contacts of the coil. This is the carbon brushes, which make sliding contact with the split ring. As the coil rotates, the carbon brushes are at rest. When the current flows through the split ring and coil, the force on the blue side is upward due to Fleming left-hand rule. And the force on the red side is downward. As the coil rotates until it reaches a vertical position, the gap in the split ring aligns with the carbon brushes. This makes no current flows through the coil, causing no forces act on the both sides. The momentum of the coil keeps it turning until the blue split ring connects to the red carbon brush, and the red split ring connects to the blue brush. This reverses the direction in which the current is flowing in both sides of the coil. This keeps the current leaving the motor in the same direction. Reversing the direction of the current will also reverse the direction in which the forces are acting in both sides of the coil. As a result, the coil will continue to rotate in same direction. So, the split ring commutator reverses the direction of the current in the coil every half turn when it is vertical. This will keep the coil rotating continuously in same direction as long as the current is flowing. The speed at which the coil rotates can be increased by increasing the current. Use a stronger magnet. This causes the magnetic field strength to increase. Increasing the number of turns in the coil. The direction of rotation of coil in the DC motor can be changed by reversing the direction of the current. Reversing the direction of the magnetic field by reversing the poles of the magnet. Candidates are expected to have a thorough understanding of the syllabus details outlined in the accompanying figure. Electromagnetic induction. Electromagnetic induction is the process that the EMF, or current, or voltage, is induced in the conductor when it interacts with a changing magnetic field. Electromagnetic induction in a conductor wire. When a wire moves upward through the magnetic field and stops, it induces current in the wire. This induced current causes an induced EMF in the wire. The needle of the ammeter deflects to the left and then return to zero. This is because the induced current becomes zero when the wire stops. When a wire moves downward through the magnetic field and stops, the needle of the ammeter deflects to the right and then returns to zero. Exchanging the poles of the magnet changes the direction of the magnetic field. When the wire moves upward through the reversed magnetic field and stops, the needle of the ammeter deflects to the right and then returns to zero. Conversely, when the wire moves downward through the magnetic field and stops, the needle of the ammeter deflects to the left and then returns to zero. When the wire moves parallel to the magnetic field, it does not induce any current. So, the needle of the ammeter do not deflects. When the wire moves upward and downward at an angle through the magnetic field and then stops, it causes the needle to deflect to the right, and then to the left and returns to zero. When the wire moves upward and downward at a right angle through the magnetic field with the same speed as before, it causes the greater deflection of the needle to the right and left and then returns to zero. We can be concluded as: when a conductor wire moves to interact with the magnetic field, causing the induced current in the wire, which also causes the induced EMF or voltage. The direction of induced current can be reversed by reversing the moving direction of wire, reversing the direction of magnetic field. If the moving direction of wire and the direction of magnetic field are reversed at the same time, so the direction of induced current remains the same. Know the induced current when the wire moves parallel to the magnetic field. Maximum induced current when the wire moves to interact at right angle to the magnetic field. We can determine the direction of the induced current using the Fleming right-hand rule. The thumb indicates the direction of force, or the moving direction of the wire. The index finger indicates the direction of magnetic field. The middle finger indicates the direction of current. 3 fingers must be perpendicular each other. The induced current can be increased by increasing the magnetic field strength, moving the conductor wire faster through the magnetic field, increasing the length of the conductor wire that interacts with magnetic field by adding more loops. Electromagnetic induction in a solenoid. When a north pole of the magnet moves into the solenoid and stops, the needle of the galvanometer deflects to the right and then returns to zero. This generates the induced current in the solenoid, which induces an induced EMF in the wire. When a north pole of the magnet moves away from the solenoid at the same speed, the needle of the galvanometer deflects to the left and then returns to zero. When a south pole of a magnet moves into the solenoid and stops, the needle of the galvanometer deflects to the left and returns to zero. When a south pole of a magnet moves away from the solenoid at a greater speed than it moves into the solenoid, the needle deflects to the right with a greater deflection and then returns to zero. This means that the induced current increases as the magnet moves faster. When the number of turns in the solenoid increases, and a north pole of the magnet moves into the solenoid, the deflection of the needle is greater to the right. This means that the induced current increases as the number of turns in the solenoid increase. When the stronger magnet moves into the solenoid at the same speed as before and stops, the deflection of needle is greater to the left. This means that the induced current increases as the magnetic field strength increases. The stronger magnet, the stronger magnetic field strength. We can conclude the electromagnetic induction in a solenoid or coil as: when a magnet moves into or away from the solenoid, the magnetic field of the magnet interacts with the solenoid, causing the induced current, or EMF, or voltage to flow in the solenoid. The direction of the induced current in the solenoid creates a magnetic field that opposes the change in magnetic field of the magnet, resulting in a force exerted on the magnet in opposite the direction of its movement. This is known as Lenz's law, which states that the direction of induced EMF in a circuit always opposes the change in magnetic field that produced it. The left end of the solenoid becomes a north pole when the magnet moves into it, creating a repulsive force that opposes the magnet's motion. And the right end becomes a south pole. The right-hand grip rule determines the direction of the induced current, with the thumb pointing along the magnetic field, and the curled fingers indicating the direction of current's flow. When the magnet is pulled away from the solenoid, the left end of the solenoid becomes a south pole, creating an attractive force that pulls the magnet back. This change in magnetic field direction also causes the induced current to reverse its direction. The direction of the induced current, or EMF, in the solenoid can be reversed by reversing the direction of magnet's motion, reversing the polarity of the magnet. If a magnet and the solenoid are stationary, it causes no the induced current in the solenoid. The induced current, or EMF, can be increased by Increasing the magnetic field strength. Moving the magnet into or away faster. Increasing the number of turn in the solenoid. The AC generator is a device that converts kinetic energy into electrical energy. It is used in power stations to generate electricity that transmitted to houses and industries. The simple AC generator is based on the principle of electromagnetic induction. Further information on this principle can be found in section 4.5.1. In a simple AC generator, turning the handle causes the coil to rotate. This interaction between the coil and the magnet's magnetic field induces a current and EMF to flow in the coil. The direction of induced current in the coil can be determined by Fleming's right-hand rule. The thumb indicates the direction of force or coil's motion. The index finger indicates the direction of field. The middle finger indicates the direction of the induced current. 3 fingers are always perpendicular each other. This is the slip rings commutator, and this is carbon brushes. The contact between the slip rings and carbonation brushes are sliding contacts. As the coil rotates, the carbon brushes are at rest. The slip rings reverse the direction of current every half turn when the coil is vertical. This produces alternating EMF and alternating current, the defining characteristics of AC electricity. The induced current and EMF can be increased by turning the coil faster, increasing the number of turns on the coil, increasing the magnetic field strength by using the stronger magnet. Graph of the EMF against time of the AC generator. The maximum EMF occurs when the coil is horizontal. This is because the coil's movement becomes perpendicular to the magnetic field. According to the Fleming right-hand rule, the induced current flows into the page in the pink coil and out of the page in the yellow coil. The induced EMF then decreases as the angle between the coil's movement and the magnetic field decreases. The induced EMF is 0 when the coil is vertical after 90 degrees of rotation. This is because the coil's movement and the magnetic field are parallel. The induced EMF then reverses due to the action of the slip rings commutator. The induced EMF then increases to the opposite direction and reaches its maximum again when the coil returns to horizontal position after 180 degrees of rotation. The induced current in the pink coil is out of the page, and the induced current in the yellow coil is into the page. The induced EMF then decreases to 0 again when the coil is vertical after 270 degrees of rotation. The induced EMF then increases to its maximum again when the coil returns to horizontal position after 360 degrees of rotation. The induced current in the pink coil is into the page, and the induced current in the yellow coil is out of the page. As the coil rotates faster, the induced EMF increases, and the time period of the alternating EMF decreases. This leads to an increase in the frequency. A simple transformer. A transformer is an electrical device that can be used to increase or decrease the voltage of an AC current. It works by mutual induction. It has 4 main components. The AC input power supply, primary coil, iron core, and secondary coil. Iron is used because it is soft magnetic material that is easily magnetized and demagnetized. When an alternating current flows through the primary coil, creating and changing magnetic field around it, the iron core is easily magnetized, so the changing magnetic field passes through it to the secondary coil. This changing magnetic field interacts with the secondary coil, inducing an alternating voltage, or EMF, in the secondary coil that has same frequency as the input alternating voltage. If the secondary coil is part of a complete circuit, it will cause an alternating current to flow. Transformers will not work with DC, because it creates a steady magnetic field that does not interact with the coil and induce an EMF. There are two types of transformers, as the step-up and step-down transformers. Step-up transformer. It increases the voltage of an input power supply, meaning Vp is less than Vs, and the number of turns on the primary coil is less than the number of turns on the secondary coil. Step-down transformer. It decreases the voltage of an input power supply, meaning Vp is more than Vs, and the number of turns on the primary coil is more than the number of turns on the secondary coil. Assuming all magnetic field lines pass through both coils, and there is no energy loss due to heating effects, the following equations apply. Where Vp is the voltage in the primary coil, Vs is the voltage in the secondary coil, Np is the number of turns on the primary coil, Ns is the number of turns on the secondary coil. The output power will be the same as the input power of supply. Where Vp is the voltage in the primary coil, Ip is the current in the primary coil, Vs is the voltage in the secondary coil, Is is the current in the secondary coil. National grid are networks of wires and cables that carry electrical energy from power stations to consumers such factories and homes. However, currents in long wires can lose lots of energy in the form of heat. The larger the current, the greater the amount of energy lost. If the current in the wires is kept to a minimum, the heat losses can be reduced. Transformers help us do this. Transformers are used in national grids, so that the electricity is transmitted as low currents and at high voltages. Typically, a large power station produces a current of 20,000 amperes at a voltage of 33,000 volts. The high current is fed to a step-up transformer, which greatly decreases the size of the currents and increase the size of the voltages. These step-up transformers increase the voltage of the electricity to approximately 400,000 volts. High voltages like these can be extremely dangerous, so the cables are supported high above the ground on pylons. As the cables enter town and cities, they are buried underground. Close to where the electrical energy is needed, the electricity is sent through a step-down transformer that decreases the voltage to approximately 230 volts, while at the same time increasing the current. High voltage transmission. When electricity is transmitted over large distances, the current in the wires heats them, resulting in energy loss. To minimize this loss, we use high voltage transmission lines. By using a transformer to increase the voltage, the current is reduced. This means we can use thinner, lighter, and cheaper cables to transmit the same amount of power, for example, aluminum cable. Alternating current is used for the transmission, because alternating current can be easily stepped up and down in voltage using transformers. This means that transformers only work with AC. Transformers will not work with DC. The calculation demonstrates why less power is lost from a cable if power is transmitted through it at high voltage. The first circuit, the power input is 2000 watts, 200 volts and cable resistance of 2 ohms. A current flows through the cable can be calculated by power equals current times voltage. To substitute, the power is 2000 and voltage is 200. The results of current is 10 amperes. When a current flows through a resistance, it has a heating effect, so power is wasted. The power loss can be calculated by power equals current squared times resistance. To substitute, current is 10 and resistance is 2. The results of power loss is 200 watts. The second circuit increases in the voltage from 200 to 2000 volts, while the power and resistance of the cable remain the same. A current flows through the cable reduces to 1 ampere. The power loss in the cable becomes 2 watts. These calculations show the power losses in a cable when the same amount of power is sent at high voltage is less than the low voltage. I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.